So my name is Dennis. As I said, I'm at DataRobot. Me and my group responsible for helping our customers to integrate machine learning models into their business workflow. So after modeling happened, after data preparation happened, we do the actual work. That's how I look at it. We also build, we help DataRobot to build these marketing apps that help us to attract attentions of the people, also help us to try new technologies, play with new toys before we go and do it for real for our customers. So without further ado, I'll do the demo. That's how it looks like, and I hope I can show the live here. I even got internet. So the app looks like this. It looks much better on the phone, and probably even better when you look on the smartwatch and on a picture smartwatch. But so during when the games are live, it's more interesting. But the closest game today is 8 p.m. So I'm gonna show you the past game from yesterday. So allows you to review it. And what we do in real time while the game is happening, and when you look at this screen, it comes up with all these three predictions, and it tries to guess which will be the next pitch. We do it completely real time. If you watch it on the web, it's actually happened ahead of time because web has a delay. So it's. And then when the pitch happens, we highlight which one happened. Sometimes we write, sometimes we not. Sometimes something happens that we didn't predict. Let me try to get to the one that we missed completely. Yeah, this one. We gave it 0 chance. Realistically, it's probably 0.01. But that's what happened. I'm gonna go and describe how we implemented it, what challenges we had while we were creating it and developing. I'll skim a little bit over data science part, but if you really want to geek out on predicting the baseball, you're welcome to stop by DataRobot table over there, and I can show you all the technical details and data prep script and all those things. So, but I'm a software engineer, and what I'm going to talk about today is mostly developing the application that uses models internally and updating it. So I'm going to go back to my presentation. So data science. So we had the pitch prediction is really good data science problem because you have a lot of data. Just for 2016, 2017, we were able to get 1.6 million pitches, so 1.6 clean data points with attributes, populated by a human. I don't think any of you ever get that kind of quality of data in your real business application. So it's a dream application. So data prep, we didn't do anything smart. We downloaded the data from the MLB API. We extracted all kind of features that they had. Pretty much everything they provided, we extracted in separate columns. The only thing that we really did on top of it that counts as a real data science, we built the historical features to show what was the proportion of pitches for a particular pitch, which one were successful, which one not, for this game and for the entire season, because we went to talk to some people in MLB, and they told us that they have a book where it's not a book, it's a tablet where they track all the pitches for particular pitches, were they successful or not, and they have sophisticated BI tool that shows it, and they use that to decide which one to throw next, because if the guy was not able to hit a particular pitch 3 times in a row, guess what? They're going to keep doing it until he hits it. So that's the only feature we built. And then to build the model, I'm going to plug advertisement here. We just uploaded to DataRobot and hit go. We didn't do any manual hyperparameter optimization or stuff like that. We just used stock DataRobot model. TensorFlow came first, so I guess if it's deep learning, it's cool. So, but XGBoost was very close behind. Our Kaggle gods told me that they can crank XGBoost and beat TensorFlow. Because usually XGBoost comes on top for majority of classification problems, at least in our experience. But this is probably one of those rare cases. So the implementation-wise, we use all the newest toys, and I'm going to explain what all those letters and logos mean for those who are not software engineers. So because this is an application that pumps data in real time from the MLB website, and it scores it and generates the features, you need some place where you can execute that code, where you can run it. And we get with with Amazon Lambda, which is a hosting that Amazon provides to run your Python, JavaScript, Java, and maybe 16 other languages. The cool part with that you don't need to think about servers and deployments. You just upload the zip file. And so MLB, they provide like 6 different types of data formats, but it's all already pre-typed data. So I assume they have an intern somewhere closed in a closet who watches the video feed and types in. They also have, I know that on some of the fields, they have this laser-based tracking system that tracks the movement of all the players and the speed of the ball and the curvature. And they actually use a neural network model to detect what type of the pitch happened. There's some famous model that they use for that, but also for other things like the names of the pitcher. And when the game happened, you can have a lot of different scenarios. To describe those, they have a person just typing it up. Usually that person is good. It's within 5 seconds of things happening on the screen, you see the data on the feed. And the feed is, the one we use is JSON feed, so it's a giant JSON document, poorly structured. I mean, it's probably perfectly structured for their website because they use the same feed to run their website, but for data science, it's a hellish. So there is a big Python script that makes it flat table, just like any data science table. So that's what we use Lambda for, just to host all our scripts that run it. So the way it works, we have a script that downloads the new data from the MLB website, and it generates the features and dumps it in a database. Then there is another script that comes around, takes it from the database, calls our DataRobot prediction servers and scores it, generates the prediction, dumps it back to the database, and then there is another script that actually serves the requests for our UI that takes all the pre-scored predictions from the database. And the database I'm talking about is PostgreSQL. So there's not much thought went into which database to use. It's just a very popular database, so we went with PostgreSQL. Redis is a very popular caching solution because we serve in potentially a lot of pages. A lot of people can visit the website in a short burst. Instead of going and generating the page every time, you use the classical approach of generating the response and caching it Redis, and then if people come back to you, you just serve from the cache, and if you generate new response, you update it in the cache. So this is more detailed thing. So what I'm talking about, so periodic scoring, the way it works for the game, we have a schedule of the games that happen, and we're getting it from the MLB website. It's also a piece of code. And we know what games are happening right now. So we have a script that goes and pulls the data for those games. We cannot update all the games because they have in their archive 10,000 games, and it's like 15 gigs of raw data. So we need to narrow it down to what's happening now. So this is the guy, periodic data ingest in the middle. So it goes talk to MLB website, gets the data, also generates all the features. And what we found very interesting is that initially, we would have a professional data scientist creating a script that uses pandas to generate the features and then use those data for training. And then I would replicate the same behavior in just vanilla Python as a developer. And it became a bottleneck really fast because I would make mistakes because Pandas is a very functional approach to describing what you do to data. You describe pretty much, mathematical function, then you apply to data, and then you get the end result. Where I was writing, classic, for loop iterative Python. And we would compare the results of applying the code, and we would have completely different prepared data on the other end. So we eventually decided just to reuse the same script that data scientist was authoring in his IPython notebook. So I had to deploy all the pandas and dependencies to lambdas. It's a little bit big, it went from 2 megabytes to 40 megabytes, but hey, it worked. The feature engineering logic actually uses exactly the same approach that data scientists use on their machine. And once it generated the data, it drops in a Postgres SQL, and then we have periodic scoring script that just monitors the database, and if it sees new pitches come in that don't have any predictions, and goes and calls the DataRobot prediction servers. And there was very interesting observation we had with our prediction servers, which could be useful to people who don't use DataRobot, has their own modeling capability. So if you expose your model to external users via REST API, make sure that REST API can do everything in one shot. One HTTP request can authenticate, find out what the model they try to score, and get all the data that you need to score. For us, it happened by accident. I don't think anyone designed it that way intentionally. But because of that, because it's one REST request contains all the information, it was very easy to put it behind a load balancer and scale up as many servers as you want. Because there is no state between the requests. One request does it all, forgets it all, moves forward. Very useful thing. Again, probably sounds very simple to people who do web development, but for people who operationalize models, could be not that simple. So if we had to do some kind of authentication handshake and then get a token and come back with a token and ask for the prediction, we couldn't build high availability infrastructure the way we built. In our case, we just sticked here between the scoring code and our prediction server and load balancer, and now we know that we always have a server that's ready to serve. Web services, these are just usual Python web services that return information to UI, the UI that you saw before. So, these screens. This is a single page JavaScript application. So it's a JavaScript application that, in English, that means that it's an application that executes inside of your browser and loads information dynamically and updates the view. So the web services that provide that information to UI here also Lambda code. Just the difference between them and the other two is that they can send a response and they can parse the parameters, query parameters. So challenges and lesson learned. So one thing that we learned really fast that literally takes, you all probably already heard that a million times, that it takes 10 times more time to prepare data than to run the model, either through DataRobot or scikit-learn or whatever your favorite tool. You spend probably a day munching the data, and then you spend 5 minutes running your model, or you spend maybe a day running the model, but you're really clicking and walking away and you're coming back. So what we learned on top of it, that once you got a model and try to build an application around it, takes even 10 times more. So we probably initially we spent a day getting the information from MLB website and building a script that flattens it out and running the model. We spent then 2 good weeks getting the first prototype of the application. And then data scientists come back and said, hey, I talked to someone from MLB and they told me that these new features we can build in will be really good, and it took us another 2 weeks to rebuild it completely. Because before, we would rely on learning information about one row, about one pitch. Previous pitch, would we predict next pitch and some historic data? He came back and said, no, we need this, slide-in window of information about particular pitcher and particular batter based on the history within this game. So pretty much I had to just throw away all my code and rewrite it. And at that point, I said, you know what, let's try to figure out how to run your Jupyter notebook on a server and turn that into our code so you can change it 10 times a day. That's one of the biggest lessons. So if you ever in a project where you build a model and then somebody asks you like how long it will take to turn it into business, take whatever time you spend building a model and preparing data, multiply by 10 and give it to your management. And I don't think that will be a conservative estimation. So that will be very real. So we've seen that over and over with our customers, but it was very interesting to feel it, ourselves on the small projects, So other thing we learned because of that, don't wait for a perfect model to start development end-to-end solution. So either of you develops a product that based on machine learning model, get dirty model using, again, scikit-learn or some linear regression model, give it to developers and let them develop their application while you playing with TensorFlow and, random forests and other toys. Because probably by the time you build the best model ever that you can build, they'll still be in the middle of their process. So it's much better to give them whatever the tools you use and give them time to figure out how to build them into their infrastructure ahead of time. So we didn't do that. We paid the price. Other thing we found out, again, it all feeds into the same topic. So use the same data format and data preps during modeling as used during prediction. So what we did during modeling phase, we used different API from MLB that provides historic data. It doesn't have real-time capabilities. It only provides the data as of yesterday. And it's much nicer XML document. XML is old and ugly, but that document actually was flat. So it took very little code to parse it out and turn it into the trainable data. Turns out it had some extra fields that the live feed didn't have. So after building a model and building all the code, and at the moment when I start feeding the real data in the model, I found out that some fields are not there. And I found out in a bad way because predictions start coming back really bad. Because DataRobot automatically backfills fields if they're missing, if they're not critical. So it's only reports if the field is critical. If it's some weight very high in a tree in a random forest, then it yells at you. Otherwise, it tries to recover. So we lost a lot of time because of it, because we were chasing it for a very long time before we realized what was happening. In particular, in this case, what happens is they have these laser and video recording of the game, and lasers give the first approximation, but after the game in the evening, somebody or in the middle of the night sits and reviews all the videos frame by frame and updates the data that lasers provided and adds a lot of additional data, like what was the angular momentum of a ball and things like that. And the model turns out picked it up as a proxy to some other behavior. So actually used those to, our model actually learned how to detect the pitch type from those movement parameters and completely ignored the previous pitch type field. But then when we put it in production, those angular momentum things were not in place and it completely ignored the previous pitch type, which is very critical for baseball to know what were thrown before. So we turned around, and what we did, we switched, we applied, I took my code that I built for real-time streaming, and I pointed on the historical data, made it scrape all the historical data, exported that information and gave it to data science. So the data science using the data is exactly the same shape and format as I see them in the code, versus have two different processes. So meaning, if you guys build a I assume a lot of data scientists in the audience, if you build a model and you build data prep code that prepares the feature for that for those models, make sure that either developers use that exact code, or take whatever code they use and ingest data using their code and then run models on them. Don't use two different codes. Again, coming back to the first item in the list. So optimize data ingest and future generation. Again, at the beginning, I thought I'm smart. I can, make this thing really fast and lean. And I made some optimization on the database side, and then the data science came back with completely different features that he wanted to generate, which completely invalidated all the funny things that I did as a software engineer. Last but not least, the philosophy that I developed towards productizing machine learning models over time is that machine learning is just another way to write software. And with that comes all the pain of writing software. I mean, create a prototype early, show it to customers first, and then go optimize it. So some long time ago, somebody taught me that first write a software, then make it work right, and then make it work fast. So the same applies to machine learning. First, get some model out of the door, show them to the customers. If customers don't understand, build your app around it. Show it to the customers, and only if they tell you they like it, that's what they need, then go and spend another 3 months tuning hyperparameters and getting the last 0.5%. Because there is very high probability that what you build is not what they need. So that's our experience. There's probably many, many more details I can talk. So one more thing, I didn't give a link intentionally because MLB we're waiting for MLB full approval to publish it. So if you were fast and saw the link, use it. Otherwise, I'm just not allowed to share it right now. Thank you.